So at this point, we should be ready to talk about Chapter 10, Nonlinear Functions. The first section, actually, I'm going to spend more time in than I am the ones afterwards. Because the first section, we need to lay all the groundwork, and I'm going to be showing you how to use the calculator, that you're going to continue to use those same steps later on. So, Chapter 10 is about nonlinear functions. When we first came in, we talked about linear functions. Now we're going to talk about nonlinear functions. And the first part of what we're going to talk about is the properties of functions. You're going to need to remember some of the skills that you've had, probably not since Math 1100. You're going to have to dredge up some of those skills like factoring and quadratic formula and graphing skills that you should have gotten before you got in here or polished after you got in here. But as we come to those, we'll kind of review and make sure that you know where you need to be. So the first thing I want to show you is a problem that kind of tells you why we want to talk about nonlinear functions. This graph is definitely not a straight line. You could probably approximate pieces of it with a straight line. For example, from 2005 to about 2000, maybe 12, that part of the function is relatively constant rate of change, so you might approximate that piece of it with a linear function, but the rest of it, you can see it rises and falls and rises and falls, and it constantly changes directions. So that's what we call a nonlinear function. This function represents the price of gold in the years 1970 through 2000, not quite 15. 15 is listed there last, but that's not, you don't quite get the point for 15 because it's only listed in 5-year increments. And then, of course, the dollars per ounce is on the y-axis, so you can read this graph and tell what the price of gold was in any particular year. So first we need to have some definitions. First of all, the definition, these are math definitions. I do not expect you to memorize them. But I'm going to give you the math definition, and then we're going to try to put it in English. A function is a rule. I have to talk about what rules are, but a function is a rule that assigns to each element from one set, which we will call the domain, to one and only one unique element from another set that we're going to talk about and call the range. Now what that means is a function might be a graph, because you can look at your x-axis, and that's your domain, and read the graph and find the y value that's assigned to that x value. A function might be an equation. It doesn't have to be a linear equation. It might be a different kind of equation, such as an exponential or logarithmic or quadratic or cubic. Those are all different kinds of equations. So the function that assigns the domain value to a range value may be an equation. You plug in x and figure out what y is. A function might be a table of values, where you read the first column and that tells you the various values of the domain, and in the second column it shows you the partners for those domain values that live in the range. So it's like an XY table. And we'll look at all those different possibilities. The domain is all the possible values of the independent value, which is the values that we always put on the horizontal axis or the x-axis. All the possible values of the independent variable in a function. That's the domain. The range is the resulting y values or dependent values that are in the range set, which is the y-axis on a graph. Sometimes the easiest way to keep these straight in your head, the independent variable is a number you put in to the equation. And the dependent variable is the number that comes out of solving that equation once you plug that number in. So here's a picture of another graph, and it's obviously, again, not a linear graph, even though very short little pieces of it might be. But for the most part, it is not a linear graph. This is a picture of the Dow Jones Industrial average at the close of business for every single day for a year in the year 2013. So on this graph, 0 back here represents January 1, 2013. And then 32 represents on this graph what the Dow Jones average was on February the 1st, 2013. And then 305, which has a corresponding Y value up here on that graph, 305 represents the closing average of the Dow Jones Industrial on November the 1st, 2013. And then at 365, we have this value up here. You notice is much higher than it was in January. That's the closing average on December 31st, 2013. So we have some questions that we want to answer about the Dow Jones Industrial Average. And we're going to use the graph to answer those questions. And in order to make it easier to do that, I've got a bigger picture of the graph so that we can answer those questions. I think this will make a good straight edge on them. I managed to lose my ruler. So the first question says, is it a linear function? As we've already stated, no, obviously it's not, because it goes up and then it changes rate, and then it goes up some more, but then it comes down, and then it goes up some more and comes down, goes up some more, comes down, goes up, down, up, down, up. And linear functions don't do that. They either constantly go up or they constantly go down. So this is not a linear function. Second question says, determine the domain and the range of this function. I want you to keep in mind that the domain is always the values on the horizontal axis. So the part I just highlighted in yellow is your domain. And we have to have a way to list all of those numbers, and we could list it out in words. We could say the domain is the value 0 through 365, where each number represents a particular day in 2013. That's actually what the domain is. But since most of the time we're asking, what are the values, what are the numbers in the domain, then the numbers go from 0, which again corresponds to January 1st, 13, and they go up to, so we put a comma, 365, which is December 31st, 2013. And since the domain includes the value 0, we will use something called a square bracket. And it also includes the number 365, so we'll use a square bracket. Those closed circles that I put in there means those last values, the very beginning and the very end value, are part of the domain. Then we talk about the range. The range values are your closing averages. And we're going to write that as an interval as well. Oh, another one bites the dust. can always tell when it gets close to Christmas, markers start running out of ink. So the range values start where this graph actually starts, which is, it's hard to tell from your copy, but it actually starts right about here. That first little bit is where the Dow closed. The Dow was actually closed on January 1st, 2013. So it had the same value on January 1 as it had when it opened on January 2. And in January 2, it didn't change very much. But over the course of that first week, it rose quite a bit, which is why this line actually starts where I put that green mark and it goes up before it continues. So its bottom value, if you notice, it's a little bit above 13,000. And since 13,000 is probably what the value of the Dow was, 13,100 was the value of the Dow on day 1, then the range begins at about 13,100. And then at the end, now that's a little bit tougher to figure out, because I've got to do my best to figure out exactly what that Y value is that corresponds to the closing value on December 1st. So in order to do that, I'm going to try to aim backwards at the Y-axis and see if I can figure out what that is. And this is not going to be absolutely perfect. I'm going to tell you that up front. You may, if I were to ask you to answer this question, your answers might be off from mine by a couple of $100 either way. Because it just depends on how accurate the graph is, how big the graph is, and how well you're able to estimate. But I do see that this is 16,000 and this is 17,000, and it didn't make it to 17,000. If I look at this as 16,500, then that looks like it might be about 16,600. So if that was the closing average on December 31st, and normally I don't put the commas in, but I did on this one, so be careful that you understand this comma is just separating the two of them. That's your set of range values, every single potential value from 13,100 to 16,600. Okay? So for domain and range, we look at both. Domain, x-axis, range, y-axis, but only the values that are actually included on that graph. Nothing else. Only what's in between here. Okay? Then the next question that we're asked is estimate f of 14. 14 would be January 14th. So the question is, what was the Dow closing on January 14th? And again, we can try to figure that out from here. Remembering that this is February 1st, and this is January 1st, the 14th is not quite halfway. So there's about the 14th day. Now, you have to be as accurate as you can. Once again, you've got a graph and you're trying to get as accurate as you can, but you're not going to be perfect. So you go to where you think January 14th is, or the 14th day, and you reach straight up to the graph, and then you read back over toward the y-axis. And again, you're going to get as accurate as you can, but it's not going to be perfection. So if I zoom in right there so you can see a little better, we see that on January 14th, which is right about here, The graph's Y value is right about there, which looks to me like it's maybe about halfway between 13,000 and 14,000. Does that seem reasonable? So
13.5.
13.5. So we think it was about 13.5. On January 14th. And again, we're estimating from the graph. So the answer is we think it's about 13,500. And then our next question says to solve the equation f of t equals 14,250, but solve it from the graph. Now the graph is all we've got, so I hope it's obvious that we're going to have to solve it from the graph. We don't have an equation for the Dow Jones Industrial Average. There is not one. So what we're saying, f of t is 14,250. That means 14,250, if this is 14.5, 14,250 is probably right about there. Okay? And what we're trying to find now, we've got the dependent value. We're trying to go back and discover what the independent value was. And the way that we do that is kind of the way we did a minute ago. We're going to draw a line from 14,250 until we see where it hits the graph. So it looks like it hits the graph about here. And that appears to be somewhere past March 1st. It looks like, by my estimation, it would probably be on day 61, which would be March 2nd. Now, if you look it up from a table of values, I will tell you that honestly, on March 2nd, the Dow Jones Industrial Average was about day 64. And day 64 would be March 3rd, I think. Let's see. I think they said it was the 5th. So maybe March 3rd. If you told me you thought this was March 3rd, I wouldn't argue with you. If you told me you thought it was March the 5th, I wouldn't argue with you. In fact, if you told me it was March the 1st, you'd still be really close. So when you're reading answers from a graph, this is where I'm trying to let you know, if your answer doesn't match the person next to you, it doesn't have to. You may see it a little differently from what they do. Your estimation, your pen might be thicker than theirs is. Okay? So, at best, this is a guess. In order to actually find when the Dow Jones Industrial Average was 14,250, we would actually need an equation or a list of all the closing values for every single day in that year. But we don't have that. Now what we have here is another representation of what we've been looking at. This is a table for the first few days of 2013. Actually, the first week in January. You notice that what happened in the first week in January is from January 1st to the end of January 2nd, since the Dow was closed, then the average remained constant. It was the same. But when it closed on January 3rd, which is the second day, then it has actually increased. Not a lot, but a little. But then the next day, it drops back down. And then it recovered and went a little bit higher. And then it stayed pretty constant for about 3 days. And then on the 7th day, which would be January 8th, it dropped again by about 50 points. Okay, and that pattern kind of continues all the way throughout the year. Now, if you're trying to ask specific questions, and if we had the whole table, we don't have, we've only got part of it. If we have the whole table, we could answer those questions better. But we don't have the whole table. This seems to imply actually that the range actually began not at 13,100, but it began at 13,104.14. But when we read from the graph, we couldn't be that specific, especially not down to 1,400ths of a point. We're going to look at some various representations now of some functions. We're going to ask the question, which of these pictures I'm going to show you, or concepts I'm going to show you, which of these are functions? So I'm going to review for you how to tell us something is a function. So that's a good, short, succinct definition of how do you know if something is a function. If you're going to memorize anything, memorize that and know what it means. Because remember, the independence, what you put in, that's the domain. And then the range is where you go when you travel from the domain. You could think of it as your domain is your house. So you live in your house. And then what happens when you leave your house is you go somewhere. You go to a different house. Or maybe you go to your retail store to work. So when you leave your house, you go to out on the range. Okay? When you leave your house, you're only going to go one place if the function that you're following is your work. You go from your home to where you work, or from your home to school. You don't go somewhere else in between. It doesn't look at any place you go in between. It says, this is where you begin and this is where you end. Because this is a function of where your planned destination is. Now, in this case, 16 left its home in the domain and it traveled to someplace in the range called 60. That was its journey. 7 left its home and traveled over to the range and went to a place called 12. And 9 did the same thing. it also traveled to 12. This does not mean that this is not a function at this point, because 7 went to 12, but 9 also went to 12. If the journey was the function I'm going to school, 7 and 9 go to the same school. And that school is unique to them, to each of those two people. And it could be unique to several other people that are going to that school that day. Same thing happens with 43. 43 leaves its home and travels to a place called 19. And 28 left its home and also traveled to 19. But 28 thinks it's special, because 28 not only traveled to 19, it has another job that it does, which is not part of this function picture, and that other thing that it does causes it to travel to 27. This shows you that this is not a function. Not a function because 28 has two destinations in the range. Sometimes it goes to 19, and sometimes it goes to 27. So it messed up the function picture for everybody. Okay? It only takes one exception. What about the x squared key on your calculator? Does that represent a function? Yeah. What makes you sure it is? Give me an example of what happens.
Because if you input like 3 squared, you're always going to get 9.
Okay. And if you put in 7, you're always going to get 49. And if you put in -3, you're still going to get 9 every time. Does it matter that 3 and -3 go to the same place? No, because they're different domain values. They're allowed to travel to the same place. But 3 can't go to 9 and -9. It has to only go to one place. So yes, this is a function. So this is a function because for any value that you use for x, there can only be one value when that x number is squared. So that does constitute a function. Does this table make a function? Colt, why do you say no?
Because 1 goes to 3 and -3.
That's right. 1 is in the table twice, but the first time it went to 3, and the next time it went to -3. Now, I don't have to look any further in that table. I can go right straight to that one single instance and say, no, this is not a function. Now, while what I just said is true, it continues to not be a function because the same thing happens with 2. And the same thing happens with 3. But as soon as you encounter 1, you say, no, this is not a function. It only takes 1 to make it say no. So all you've got to do is find the exception. Now these two sound very much alike, so we're going to have to be careful what is the domain and what is the range. The domain, which is represented by being the first elements, the domain is the children and the range, which is always the second element in ordered pair, is the children's birth mother. Okay? Is that a function? How do you know for sure it's a function?
Because you can have like the same child twice. You go with their parents.
Well, you can't, well, you sort of technically can, I guess, if you talk about twins. But the point here, you have how many birth mothers? Everybody in here, how many birth mothers do you have? One. Now, you may have another mom, you may have another mother, either one that you took up with, maybe it's a grandparent, maybe it's that you were adopted and you have a birth mother and a mother that raised you, but you only have one birth mother. Everybody only has one birth mother.
Which one is that, Miss Flynn? D?
That's D. Everyone only has one single birth mother.
This one's
They're
really
backwards in the
different.
notes.
Are they backwards in the notes?
Yeah.
Okay, well, pay attention to the words and be sure that you put this with the correct one. So this is the one where it's the children and the mother. That's the way the ordered pair writes. So that is a function. But now we're going to switch things up in the next part. In the next part,
Only has what? One birth mother?
one birth mother. In part E, it sounds a lot the same, except in part E, the first element is the children's mothers, their birth mothers. So part E starts out with the mom. And then the second element is the children. So the order of this one is mother-child. Does that constitute a function?
No,
Why not?
because the mother can have more than one child.
That's exactly right. The mother is the domain value. The mother is the one that is producing children, but every mother can produce more than one child. And some mothers don't produce any children, which I guess technically means they're not a mother. But there's nothing that says there has to be a range value for every single domain value. Some domain values may not have a value in the range, because for whatever reason that range value might be, and we'll talk about it later, it might be undefined. But a mother can have no children, a mother can have one child, she can have two children, she can have 10 children. So because of that, this is not a function. It's not a function because a mother can have more than one child. Okay? And hopefully as we go through these examples, it'll get it kind of lined up in your head, what it takes for something to be a function. And you'll be able to apply that to equations and graphs and things like that. Here's a graph. Is this first graph a function?
Yes.
Okay, I have a yes. If you think it's no rather than yes, tell me why you think it might not be. What do I need if I'm going to answer no? I need one single x value that has two y values. Does that happen?
Shouldn't happen because it's going to be infinity.
That's right. This graph actually continues to go down this way.
So you should never have anywhere where it crosses twice.
That's right. You shouldn't have any place where, let's say, let me look at the x value where x is -1. Well, that means the y value is right there. If I plug in y equals 11 minus 4 times -1 squared, that means the y value is 11 plus 4, or I don't think it's 15. I think I must have messed up. No, it's -4. Sorry, that I did mess up. -1 squared is +1. So it's -4, and 11 minus 4 is 7. And that looks a lot more reasonable. Okay? It can't have any other value other than 7. Now the fact that I go over here to +1, if I plug in +1, I'm still going to get 7. That's not a problem, because these are different x values. This is your domain values. And the same thing if I were to use, let's see, 1, 2, 3. Let's try 3, because I can actually hit pretty close on 3. So if x is 3, three squared is 9. And my y value is -25. And there's no way to get anything else. So the graph is a function, but also that equation. The graph's just a picture of it. That equation is a function. Okay? Here we've got another graph. The graph is x equals y squared. Now, if x is 0, y squared is going to also, given that this is y, it's also going to be 0. So that's 1 to 1. But if x is 2, what you see from reading the graph is it's got one value here and a different value there. Same thing happens if it's 4. 4 is partnered up with 2, but it's also partnered up with -2. So that is not a function. Because there are x's. In fact, all of the x's except 1 have 2 different y values. Okay? What about this one?
Yes.
Yes, it is a function. It's a function even though the domain goes from negative infinity to positive infinity, which we say in words as all real numbers, but it only has one single range value, and everybody has that same value. So when you only have one single range value, you put it in little curly brackets and say, this is all there is, folks, this is it. Okay? But the fact that everybody goes to 7 doesn't matter, because that's still a function. Every single x has one value. And that single value is 7. Okay? Is this a function?
Yes.
Yes. Because as you move across this line for this function, every x has exactly one y. So that's why it is a function. And just for the practice, domain and range, your domain, if you go straight down to your domain axis, begins at -1 because that circle's closed. And it ends at 4 because that circle's closed. And when the circles are closed, you always use a square bracket to write your domain interval. So the domain is from -1 to +4 with square brackets on both. And then your range values, since as far down as this goes, is 0, and as high as it goes is to 3, then my range is everything in between. It includes 0 all the way up to and including 3. So you should be able to look at a graph and tell what the domain and range are. Yes?
You said when denoting domain and range, if it is just a value, a definitive value, that's when you use the bracket?
Use little curly brackets. Or if you don't really like the symbols, I don't know if my math lab makes you use the symbols or not, I don't remember. But for me, as long as you say the range has only one value, 7. You don't have to memorize symbols for me. You have enough foreign language to deal with in this class as it is. Okay? So practice finding domain and range. Is there any number that you cannot put in for x? Any number whatsoever that you couldn't plug in for x and get f of x?
0.
Well, if you put in 0, f of 0 is 0 squared, and it's still 0. So we could do that. Maybe it's time to go back to the PowerPoint and remind you of the 2 cardinal sins in math.
Is it negatives?
What that says in the top box is math language. I'm going to put it in English. There's 2 very important commandments in math, especially in algebra. Thou shalt not divide by 0. You cannot divide by 0. It is not possible to divide by 0. Ask your calculator, it'll tell you. Try to divide something by 0 and see what it says.
Cannot divide by 0.
It says, nope, can't do that. Second one says, thou shalt not take even, meaning square roots, fourth roots, sixth roots, anything where the root on a radical is an even number. You shall not take even roots of negative numbers. And the reason that you can't take even roots of negative numbers is if you're trying to take the square root, for example, of negative 16. Is there any way to multiply two identical twin numbers together and get negative 16? No. If you multiply 4 times 4, you get positive 16. If you multiply negative 4 times negative 4, you get positive 16. So you can't take the square root of a negative number because the fact that it's negative says one of its factors was positive, one was negative, and therefore they are not squares. Okay? Those are the only two things you need to worry about. No zeros in a denominator, and no negative numbers under an even radical. It has to be an even radical. You can take the cube root, for example, of negative 8, because negative 2 times negative 2 times negative 2 is negative 8. So you can take cube roots of negative numbers. You can take fifth roots, seventh roots, ninth roots, anything where the index is odd, you can do it, but only if it's even. Okay? So going back to our examples, what I want you to do here to be able to answer the question, what is F's job? What does it do with X when you give it to it? When I give it an X value, what does F of X do to X? Just in English words. What does X squared mean?
Wherever you put it, it'll come back out.
Means square.
Well, but what does squared mean in English? What is the squaring process? Just tell me in words.
Multiply it by itself.
Multiply it by itself, okay? Multiplication. This is just a different way of saying multiplication. So is F's job, is it ever going to divide anything? Given that this is what it says it does. No. F's only job is to take what you give it and multiply it by itself. It does not divide. So we don't have to worry about that. It does not take square roots or fourth roots or any other roots. It doesn't do any roots. So unless you see division or a root, there's no problem. Okay? So the domain here is going to be all real numbers. That's negative infinity to infinity. The range, because you can put in anything in the world you want to for the domain, the range is going to be the same. Negative infinity to infinity. Now the next question is very, very similar to that. It says y equals x squared, which is the same thing as a. Just we're calling the function y. But it has a specified domain. This is the domain. And notice it has little curly brackets because it's a list of numbers. The curly brackets indicate that it's just a list of numbers. It's not an interval. So if the only numbers that this function gets to work on are negative 2, negative 1, 0, 1, and 2, what would its range be?
2 and 2.
Okay. What happens if I square negative 2? You get 4. What happens if I square negative 1? You get 1. What happens if I square 0? What happens if I square positive 1? What happens if I square 2? So the range values, since you don't really need to write 2 4s and 2 1s, the range values are the set of numbers 4, comma, 1, comma, 0. And you could write it in the other order. You could write 0, 1, 4. But you just have to be sure you've got all those range values in there. The fact that there's a restriction on the domain restricts what you can have in the range. What do we need to watch out for here? What could be a problem? Whatever this is, because this is a root function, that can't be negative. That is not allowed. No negative. Okay? So in order to figure out what would cause it to be negative, we're going to actually write an equation and make it negative. This basically, if you're less than 0, that means it's negative. And if I solve this equation by adding x to both sides, I come out with 6 is less than x, which is the same as saying x is greater than 6. So any number greater than 6 will make this have negative numbers. And we can actually verify that. Here's 6, 5, 4, 3, 2, 1, 0. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. And here's 7, 8, 9, 10. So if I say 6 minus 0, I get 6, right? And the square root of 6 is okay. If I say 6 minus 4, 6 minus 4 is 2. And the square root of 2 is okay. If I say 6 minus, let's see, 1, 2, 3, 4, 5, negative 5, 6 minus negative 5 is 11, and the square root of 11 is okay. So all of these numbers are okay, including 6, because 6 minus 6 has me taking the square root of 0. But what if I were to try to plug in 8? 6 minus 8 is negative 2. Can't do that. Okay? So your domain starts at negative infinity and goes up to and includes the number 6. And if you look at a range of values, what you see happening here is this starts out at 0, then the square root of 2, square root of 6, square root of 11. It gets bigger and bigger and bigger and bigger. So your range is going to start at 0 and include 0. So we'll put a square bracket. And it goes to positive infinity. So there's your domain and range for those two. What about D? Ask yourself the same question. What does f of x do with x? What's its job? It takes x and squares it. Then it multiplies it by 2. And then it multiplies it by 5 and adds it to what it got in the first go around. And then from that total, it takes 12 away from it. Okay? So, are there going to be any problems in the domain? No, we're never going to divide. We're never going to take a square root or a fourth root. So the domain is all real numbers. The range, however, is not. The range is not. And in order to see what the range is, I'm going to go to the calculator here for just a minute so we don't have to do arithmetic. And I'm gonna enter in 2x squared plus 5x minus 12, and set the table up and just let it run. And what I see here is it's positive to the left of -4. It's negative from 4 until it gets to 2, and then it goes back to being positive. At -1, it has the value -15. So if I were looking at the table, I would say the range goes from -15 to infinity. Now, that's not actually the right answer, I will tell you that. That is not actually the right answer. But from the table, that's the best we can get. What we're going to do is I'm going to pick up here next time and explain to you that we can actually do something we're going to do in the next chapter and figure out exactly where the bottom of the domain is. So this is best guess from the table. Okay? So we'll pick up there, and then we'll go into 11.2 next time, so make sure you have your notes ready. Yes. Yes.
What if we did take the test for chapter 10? Or just for the, like as a class?
As a class?
Yeah. 'Cause I feel like we would learn the chapter 10 better if we didn't have a test like focused on the final. We could still be tested on the final.
You will be tested on the final.
But and chapter 10 will be on the final, right?
Chapter 10 will be on the final, but here's my issue with it. I need to know, before I see you in January, whether or not you can do chapter 10, because if there was the most important chapter for calculus, this is it.
I feel like though, I mean, we have a lot of, like our other classes have a lot of work, and there's 5 sections of homework with 20 questions, and the quiz on Shobi's 30 questions, and then we have Shobi work. That's a lot of work to do for one
The
chapter.
Shobi homework for this chapter, usually there's 1 or 2, maybe 3 problems.
There's 5 for both chapters, 10.1 and 10.2.
5 Shobi homeworks?
Yes, ma'am.
I'll go look.
They got a bunch
I thought,
they got A, B, C, D, E on
I'll go look, but there shouldn't have been that many. I only remember putting in 2 or 3.
That'd be kind of hard because you have all the homework, and you said it's going to take like 2 hours for chapter 10, so, and we only have 2 weeks, and then finals for other classes.
Well, but your test over chapter 10 is going to be outside of class.
That's what I'm saying, though. We got to do the other stuff outside of class too, though, so we got to find time to do that.
Go look at your My Math Lab homework before you worry too much about it.
I've already looked at it.
Okay, so a lot of it is multiple choice.
I've already did all the multiple choice, but I still have 50s and 60s and all of it. And we have.
I'll go look at it and think about it,
All right.
okay?
Thank you.
Just